This is just a short video to summarize all of the transformation rules for transforming trig functions. So this works interchangeably for sine and cosine, but just for the sake of this video, I'm going to do the sine function. And so what I wrote up here is just the different ways we can manipulate these functions, right? So there's a number that we can go out front here that can be positive or negative. We can have a number next to the x that can also be positive or negative. Again, c and d can also be positive or negative. And I wrote it two different ways, right? So most of the problems we've done don't have this term here. So you just have a term here that's going to change the period, but you don't have this one. So this term ends up moving left and right. But the key here, and the thing I want to emphasize, is you're not going to move left or right by c as you would expect here, right? So here we move up or down by d, but you need to factor out this b term in order to know exactly how much to move, right? So that's why I wrote it out this way, okay? So this is a slightly different thing, but if you factor this b out, this c now, it's slightly different, but that'll be how much you move left and right. So those of you on IXL, it had that weird, like, what was it, C over B thing. And so that's essentially what they're getting at, is factor it out. So I encourage you to always factor that term out, and I'll summarize everything and give some examples. So here's kind of the summary of all the terms, right? So A is the amplitude of the function, and you can find that by looking at the max minus the min. I'm talking about y values here, and if you divide that by 2, you'll find the amplitude. The period, right, is kind of what B is helping us to find. So the period is the distance that it takes the wave to repeat itself. So you can find the B term is just 2 pi or 360 if you want to work in degrees, divided by that period that you can calculate on the graph, or you'll be told in the problem. C, remember, is left or right, but only if things are in the factored form. All right, so right here needs to be factored, and D moves up and down. And a neat way to find D is to take the max and add it to the min and divide that by 2. And that'll tell you where the center line is. So that'll tell you how much you move up or down. And then the final thing I want to bring up is that if A is negative, so you put a negative in front of the A, you're going to reflect the whole graph over the x-axis. And if B is less than 0, you're going to reflect over the y-axis. So now what I'm going to do is just move this out of the way, and we'll go through a couple examples. So let's take a look at the graph at the right, and we'll try and come up with its equation. So the two easy ones to find are the amplitude and what I'm calling D, which is the up or down movement. And so following the formulas above, we can see that the amplitude is 3, and then we're going to have to move the function down 1. Next, I'm going to calculate the B term. And so we're going to use that formula that the period is equal to 2 pi over B. And if we rearrange that to solve for B, we can see that the period itself is going from 0 to pi, right? The peak to peak there, from here to here, that is one wavelength. And so that's going to be our period, which is pi, which lets us calculate B to be 2. So now we have a function that looks like this. And now it looks like a cosine function, and we in fact could write this as a cosine function. But in order to practice moving things left and right, what I'm going to do is make us write this as a sine function. So that means that the C is going to have to do something here. So our normal sine would usually have this midpoint here, kind of the midline, right, on the y-axis. So if you picture that, it would have been, say, somewhere here. In order to get this curve we have to move to the left, right? So we're going to have to move everything to the left, which means we're going to do a left shift. So what I'm going to do to make this a little easier is I'm going to factor out the 2. Now keep in mind, strictly speaking, these are two different C's, but I'm going to use this factored version in this case. So what we have to do is figure out how far we need to move. And so hopefully you can picture this curve is symmetric about some vertical point here, and that the midpoint between 0 and pi over 2 is going to be where that midline is going to cross the y-axis. So we're going to need to move left by that amount. And so what we can do is just do pi over 2 minus 0 over 2, which is pi over 4. And so that's our total shift, so we can plug that in. And so this is the result we'll get. And notice we had to factor out the 2 in order for that to work. So this time, let's go the other way and look at the equation and see if we can try and graph it. So the first thing I'm going to do is just try and identify A, B, C, and D. So going through and following the stuff from the previous screen, we can use A, B, C, and D to tell us how this graph is going to change, right? So A is clearly 2. It's positive, so there's no flipping, so the amplitude is 2. B, right, we can use B, that we can see that's 3, and we can use that to find the period. So the period this time is going to be a little different. It's going to be 2 pi over 3. And then this part, to find C, remember, we need to factor. So this is the factoring step, just to make sure I pick the right C. And so here C is going to be pi, which means I move right pi because it's negative. And then D is 1 right here, and that means we move up 1. So let's just move this out of the way, and I'm going to draw a grid for my graph. So here's a grid we can work with. So the first thing I like to do with these complicated ones is use the amplitude and how far up and down I move to kind of find where my graph is going to live. So here, if the amplitude is 2, that means I can go down 2 and up 2. So that means I'm going to have kind of a height total of 4, and I'm going to move up 1. So if I was centered at just around the x-axis, right, I would go up 2 and down 2. But here, I need to move up 1, so I'm actually going to go from -1 to 3 in this case. So I'm going to draw some dotted lines to indicate that. So I chose to make each square half a unit, so that way we can know that our curve is going to be somewhere in this area here. And then I'm also going to draw the midline so we know where our center is. So often when you're doing it this way, it's easier to draw 2 versions. So I'm going to draw one version without the horizontal shift, so I can just make sure I get everything right. And then I'll shift it, and we'll see where we end up. So let's just graph y equals 2 sine 3x plus 1. Okay, so what I've done here is I marked the initial point where I'm going to cross the y-axis, right? Yes, the y-axis. So a normal sine curve, right, would start here and go up and then down and up, right? Here, I've got the sine curve, but I'm going to change my amplitude, which we already took care of with the blue dotted lines, and I'm going to have to move it up 1. So that means I'm starting at the green line. So I'm going to start here and go up and then down and then up. Now, my period that I know from this part is 2 pi over 3. So that's why I chose to label my x-axis this way. So I'm going to make every cell horizontally be pi over 6. So that way I know if I'm starting here, I need the whole wave to repeat itself by 2 pi over 3. So I know I'm going to be back at the midline at 2 pi over 3. And then what you can do is you can break every wave into 4 pieces, right? So you've got from the midline to the peak, from the peak to the midline, from the midline to the minimum, and from the minimum back to the midline. So what you can do is break this chunk down into 4 equally distributed distances, right? So halfway between 0 and 2 pi over 3 is pi over 3. And then if you go up pi over 6 in either direction of that, you get those. So that means if I start here, I need to peak by pi over 6. And then I need to be back in the midline by pi over 3. And then I need to come back down at a minimum at 3 pi over 6, which is pi over 2. And then at 2 pi over 3, I'm going to get back to the midline. So let's draw that in and see how it looks. So this is the best I could do, but it should be nice and curvy. And that's what y equals 2 sine 3x plus 1 will look like. And obviously, it's going to continue off after that. But I just wanted to give us one wave. So that's one way to graph that. So now we need to look at what happens when we shift this thing to the right by pi. So I just extended the curve a little bit so we can see. But basically, if I shift to the right by pi, I'm going to have to put this point all the way over here. All right. So I'm moving by 1.5 wavelengths. So the net change is just going to be moving right by 1/2 of a wavelength. And so if we look at our wave, right, so that is 1/2 of a wavelength. So we need to move over 1/2 of this wavelength. So what should happen is we should see that this peak now moves over to pi over 2. So I'll draw what happens after we do the shift. So here's what that should look like. So we moved over by 1/3 of a wavelength. That was our net change, right? Even though I'm really moving it over by more than that, we were canceling out an entire wavelength, which is fine. So that's going to be our net result, is this green curve. All right, so that's one way to do this. So in summary, first I would graph it without the phase shift, without the left-right movement, and then just figure out how many wavelengths you shifted left or right by, and then do your final change.